Alvarez-Gavela from MIT, who will talk about caustics of Lagrangian homotopy spheres with stably trivial Gauss map.
Okay, so let me just share. Yeah, thank you very much to the organizers for the invitation. Right. Let's see. So can you see? Yes. Yeah. Okay. So yeah, I want to talk to you about a small, just a small paper that we put out yesterday. So let me just tell you two things about it. So the first one is that this is really an IOU from my PhD thesis. So, in my PhD, I did an H principle, and the H principle, you typically reduce a geometric problem to a homotopical problem, and then you sit back and you're very happy about it. But really, homotopy theory can be hard, and the homotopical problem is still not. I don't understand it for arbitrary manifolds. But what I want to do today is explain the solution of the homotopical problem in the case of spheres. So it's a small amount of homotopy theory that needs to be done, but I just somehow didn't have time to do it in my thesis. So what I did is I assigned it as an undergraduate research project to an undergrad, David Darrow, or rather, I assigned to him the exceptional dimensions. You'll see that there's something different that happens in the dimensions 3 and 7 because of the parallelizability of those spheres. And like a different argument is needed. It's a very hands-on argument, and that's the argument that the student wrote up. So that's the plan. Well, yeah. So that's what I wanted to tell you about it, and then let me start. So let L be a Lagrangian homotopy sphere. So it's a Lagrangian submanifold with a homotopy type of a sphere. And as usual, just interrupt me if you have any questions. Just unmute yourself and speak out, please. And I have gamma, which is a Lagrangian distribution. Okay. And then the central notion for today will be the notion of stable triviality. So I say that gamma, and I really only care about the restriction of gamma to L, is stably trivial if, when I stabilize it, it's homotopic to the stabilization of the tangent distribution to L as Lagrangian distributions in the stabilized symplectic bundle. Okay. And then our theorem is the following, that the tangencies of L with respect to gamma can be simplified to consist only of fold via a Hamiltonian isotopy if and only if gamma is stably trivial. Okay, so I will compare this theorem to just what you get from the H principle, but let me just make some remarks, and if you have any questions about the statements, please don't hesitate to ask.
Yeah, Danny, are you going to remind us what a fold is?
Right. So first remark: a fold is the simplest tangency. So it's the simplest possible tangency you could have, and it's locally modeled on a parabola, stabilized. And gamma is just a vertical distribution. So the picture looks like this. This is your L, and it's just a quadratic tangency with respect to the red distribution gamma. So that's what a fold is. Now, let me remind you, and let just consider the case where L is a standard sphere here, so we don't have to worry about exotic spheres for a second. That although it's true for any L, that the tangent bundle to the cotangent bundle is a trivial symplectic bundle. So we can view gamma as an element of pi n lambda n, where lambda n is the Lagrangian Grassmannian, and then stable triviality is means that you belong to the kernel of the stabilization map induced from the corresponding stabilizations for un and on. And in terms of Lagrangian, linear Lagrangian subspaces of Cn, that just means direct summing with R inside another factor of C. Yeah, and then let me say one more comment, that this group, once I stabilize once, is stable, is in the stable range, and bot compute this in the stable range, and in particular it's trivial for half of the residue classes modulo 8. So for those classes, there's no hypothesis in the theorem. Okay, so those are the remarks. And any further questions about the statement? Okay. So what did I do in my thesis? Well, I proved some similar statements. So let me be lazy and just, I'm going to copy this and paste this. So what I proved is that you can simplify the singularities if and only if gamma is homotopic to a gamma prime, such that the tangencies of L with respect to gamma prime are only folds. So what the H principle says is that you can simplify the tangencies to consist only of folds via Hamiltonian isotopy, if and only if you can do it via a homotopy of the Lagrangian distribution. So the geometric statement reduces to a homotopical statement. And the novelty of this theorem is to characterize when the Lagrangian distribution can be deformed to have only folds. Namely, this happens if and only if it's stably trivial. Okay. And therefore, the theorem that I wrote today reduces to the following purely topological statement, which is that every element of the kernel of this stabilization map admits a representative so let me write it like this, as a map of pairs with only fold tangencies. Okay, so this is really what we're actually trying to prove. And then by the H principle, it implies the theorem that I wrote at the beginning. I'm going to make a remark that it will actually follow from what we do that that this kernel is always cyclic. So I can't believe that this was not known. I'm sure it was known, and I'm sure it's in the literature, but I just couldn't find it. So we were proved it if it was known. And in any case, it's not particularly hard to prove. It's just you have to do some diagram chasing. But in any case, that's what the kernel is. It's just cyclic, and we will exhibit explicit generators in each case and show that the generator only has folds. In fact, the generator is given by just a sphere of folds. Okay, so that's my introduction, and then before I actually give you the proof, I'm going to give some applications. So any questions before I talk about the applications? Okay, so for the first application, let W be a Weinstein manifold. Let's say Weinstein domain. And I want two properties. First one, I want it to admit a polarization. And two, I want it to be a Morse-Weinstein manifold, but a very simple one. I want it to have just two critical points, and one of them is going to be a minimum. So really just one handle. Okay. So then immediate corollary, well, not quite immediate, but almost immediate corollary is that it can be arborealized. So don't worry too much. If you don't remember what an arboreal skeleton is, we'll see what's relevant about it in a second. But let me just make some remarks. So this recovers a special case of more general result that we proved with Eliashberg and Nadler, in which we don't have the assumption 2, so we just did it for arbitrary polarized Weinstein manifolds. However, that treatment is rather more complicated. And the reason is that there's difficulties which arise from the interaction of 3 or more strata. Whereas in our case, the initial skeleton, although singular, only has 2 strata, one for each critical point. And so what we can do in this particular case is that we're going to use Starkson's strategy. Which she used to arborealize 4-dimensional Weinstein manifolds. So it's going to be arborealization a la Starkson, and let me just quickly explain the proof. But so any questions about the statement, modulo the fact that I haven't explained the most important word, which is arboreal? Yeah, I kind of don't want to get too caught up in this, so maybe just think of arboreal as a reasonable class of singularities. So let's just do the critical case because the other one is easier. So let me just quickly remind you what Starkston's strategy is. So so your skeleton at the beginning is like this. You have some minimum, and then you have a critical handle, which is attached along some Legendrian, and then the skeleton is the cone on that Legendrian. So that's at the beginning. And then what one does is one blows up that ball, that Darboux ball around the minimum, to a Morse-Bott disk. Okay. So now lambda is in the cosphere bundle of a disk. And if one just does this, this projection, it's a front projection and has absolutely terrible singularities. Okay, but it's not hard to see that existence of polarization. Well, let me just actually spell it out. So without loss of generality, I can assume that my global polarization is the kernel of d pi on this blue part. And then the restriction of gamma to lambda is the Liouville direction plus z. Sorry, the Liouville direction plus v, where v is tangent to the cospheres. So singularities of the front correspond to tangencies with nu. And the fact that nu direct sum z extends to the whole unstable disk of xn precisely means that the class of nu restricted to lambda is stably trivial. Okay, that disk, that extension to the disk gives you a null homotopy. And so theorem applies. Okay, and so we apply the theorem. And what do we get? Well, what we do is now we deform this this Legendrian so that the projection is now real nice. So maybe it just has cusps. And then finally, Starkson wrote down a model for the arborealization of the semi-cubical cusp, which in a oversimplified manner consists of replacing the semi-cubical cusp with just like an arboreal singularity like this. And you have to be a little bit careful because this propagates up in the Liouville direction, and then you have to make it land on some wall upstairs. So it's not entirely local, but it's a semi-local procedure. But whatever, you do some you do some local model in which you replace the semi-cubical cusp by some simple arboreal singularity, and then you have a skeleton that is nice and simple and only has arboreal singularities, and the theorem is proved.
Okay, so I'm sorry, I know you said you wouldn't go into it, but just to understand the syntax, arborealization is when you find the representation where the singularities are arboreal, which is a very nice kind of singularity that
Correct.
you can then work with.
Correct.
Gotcha.
Yep. Yeah, so whatever arboreal singularities are, there are a nice class of singularities for the skeleton. And here, what you do is first you construct a skeleton where the singularities are just given by so if I only have folds with respect to nu up here, then that means that the front downstairs only has cusps. So folds up here corresponds to fold to cusps down there. So by the theorem, we managed to have the front projection only have cusps, and then we traded those cusps for whatever simple singularity the local model tells us, and it's
Something simpler even than cusps. That's
impressive.
Something even simpler than cusps. That's impressive.
Well, I mean, depends on. They're simpler for some purposes, and cusps are simpler for other purposes. So, yeah.
Makes sense.
Yeah, cusps are nice. I don't have anything against cusps, but okay. So that's the first application. Any other questions?
Is there some kind of classification of some class of Lagrangians in these Weinstein manifolds using your result? I mean, you're using it for this particular.
I don't think you'll achieve any classification of Lagrangians using this, as far as I can tell. Not to my knowledge, at least.
Thank you.
Yeah. Yeah, I don't have anything more to say. Because yeah, I mean, this is just telling that the local structure is very simple, but the global structure might be Might be very complicated. A little bit in that spirit, let me say another application in which also I will prove something, but it won't necessarily imply much, at least a priori, about the classification. So let's take a nearby Lagrangian. So that was one application. Let's go to the next one. So let L be a Lagrangian homotopy sphere. It implies that sigma is also a homotopy sphere. And then a corollary from the theorem is the following. There exists a Hamiltonian isotopy such that the time one flow of L is generated by a framed function on a tube bundle. Okay, so let me explain these words, and then I'll sketch the proof. So a tube is up to a compactly supported isotopy the result of a standard handle attachment to a half space. Let me do this capital N. So what is a standard handle attachment? Well, it looks like this. And then what's a tube? Well, maybe it's like a little funky, but it's just something obtained from the previous thing by a compactly supported isotopy. So anything of this form will be called a tube. So that's a tube, and a tube bundle is a bundle of tubes. And what is a frame function? It's defined on a fiber bundle and on the total space of the fiber bundle. And it has the following two properties. First of all, the restriction to every fiber is Morse or generalized Morse. And two, the negative eigenspaces are framed. So the negative eigenspaces of the Hessian at the fiber-wise critical points okay, and they're framed, so each one of them has a framing, and the framings vary continuously over the base and are suitably compatible at birth-death points. So frame functions are important in geometric topology because they are the homotopically canonical way of studying smooth fiber bundles via parametrized Morse theory. Okay, it's a theorem of, well, Igusa and Eliashberg and Mishichev that on a fiber bundle there's a unique frame function up to homotopy. In fact, the space of frame functions is contractible. So they're the homotopically canonical way of doing Morse theory. So
Danny,
that, yeah.
so when you say that you have a tube bundle, is it tube bundle over sigma?
Yeah.
And generated means you pick up the critical points of the family of Morse functions?
Yeah, generated means that,
values, I guess.
Yeah, in the usual sense of generating functions. So,
okay.
so the one, yeah, yeah, it's generated by the function. Okay. So let me explain the proof. So first of all, and just before we get too carried away, all of the heavy lifting here is not done by us. So all of the heavy lifting is done by this recent, in my opinion, absolutely fantastic theorem of Abu Zaid, Kurt, Guillermo, and Kra. Okay, and what they prove is that it admits some generating function on some tube bundle. Okay, and so what this implies in particular is that the Gauss map of L is null homotopic. And therefore, that if you trace down the definitions, it means that our theorem applies. Okay, and therefore, there exists phi t such that phi 1 only has folds, fold tangencies with respect to the vertical distribution. Okay, but now we apply the Chekhanov homotopy lifting property for generating functions. So by this theorem, the time one flow also admits a generating function on, well, a stabilization, but that's fine. Stabilization of a tube bundle is still a tube bundle if you stabilize appropriately. And then notice that so let's call this stabilization of W, F. The restriction to each fiber is Morse, or generalized Morse. Why? Well, because if you look at the Lagrangian projection, a fold of the Lagrangian with respect to the vertical distribution corresponds to a semi-cubical cusp with respect to in the front projection. And you can check that if you look at what can generate a semi-cubical cusp, it's only a birth-death of Morse critical points. So just for free, you get that the restriction of this function to every fiber is Morse or generalized Morse. And then to frame F, you might not be able to, but you can replace this bundle with a twisted stabilization. So basically, this function might not be frameable, and there's an obstruction to that. But oh gosh, we're gonna get into this. Yeah, I'm sorry, Claude. Let's see. Theoret's vibration theorem. Thank you. Yeah. Oh, I see this direct message. Yeah. So Chekhanov theorem, Theoret's vibration theorem, the homotopy lifting property for generating functions. I'm probably using the form for vibrations at infinity. I always have problems with this reference. So yeah. Okay. Theoret's theory. Thank you. Okay. So what was I saying? Oh yeah, so you replace it with a twisted stabilization using the fact that the projection is a homotopy equivalence. It's proved by Abu Zaid. And that's basically the whole proof. So it might not be frameable, but there's an obstruction to doing that. But because the projection to the base is a homotopy equivalence, I can actually undo that obstruction by stabilizing in a twisted way. And in the paper by Abu Zaid, Guillermo and Cry, it is explained how to do twisted stabilizations. So that's the proof. And now if with our boreal singularities and nearby Lagrangians we were getting a little bit messy, then don't worry, because I'm about to completely change gears, and then the rest of the talk is just going to be classical algebraic topology from the 60s. So I'll just pause here for questions. But yeah, this is now we're going to just do very elementary stuff. And any questions? No questions? Okay. So let's prove the theorem. Let's prove it for n not equal to 3 and 7. So we will use the fibrations O(n) to U(n) to lambda n and the stabilization maps and the long exact sequences in homotopy associated to these fibrations. Okay. And the main technical lemma, I mean, it's a joke calling it a technical lemma because it's just a page and a half, but whatever, you have to prove something at some point. But for n not equals to 1, 3, and 7, we have the following, which is that if you are a Lagrangian distribution that is stably trivial, and the underlying vector bundle is trivial, then you're actually trivial as a Lagrangian distribution. So let me just remark that the image of a Lagrangian distribution in pi and lambda n in pi n minus 1 O(n) is just a clutching function of the vector bundle. So this is just the underlying real vector bundle. So it's saying that if the underlying real vector bundle is trivial and the Lagrangian distribution is stably trivial, then in fact the Lagrangian distribution was trivial. And the proof is by cases modulo 8 using the literature on the homotopy groups in the stable and metastable range. So in particular, this uses results of Bott, Curver, Milner, and Kachi.
Right. So when you say n is not something, you mean mod 8?
By cases modulo 8? No. I
in the
actually
statement of your
mean n not equal to the three numbers 1, 3, and 7. Yeah.
But then you analyze how does that work? Like if you
We'll deal with those cases later. The strategy that I will explain now just does not work for those dimensions.
Okay, maybe I should let you finish
This lemma is not true. This lemma is not true for n equals 1, 3, and 7.
I understand. It's just so far the proof looks at you're saying it works modulo 8. So I wonder how you do the transition to concrete values.
Yeah, I mean, we will deal. We'll do it later, but we'll do with the cases 3 and 7 using explicit argument using quaternionic and octonionic geometry. Yeah, the just abstract arguments that I could find just don't work for those special dimensions.
Okay, I see.
Yeah. Okay.
I think what Sarah meant is if you're only arguing modulo 8, how do you distinguish 1 from 9?
Oh,
that was her point. No.
Yeah. Well, what happens is that these groups are 0. Yeah. So these groups are 0, but in general they are not 0. Like for residue classes, for the same residue classes modulo 8, but bigger than 3 and 7. These groups are not 0, but because of the parallelizability of S3 and S7, these groups are 0. So the argument breaks down. Yeah. So that's what's different in these cases.
Thank you.
Yeah. Thanks. So yeah. So then I need another lemma. So first, let me give you a definition of Michael Entov, who was here before, maybe he's still around. So a formal fold is the simplest version of his notion of a chain of singularities, and it consists of two pieces of data, well, these are formal folds in Rn, so I just need a smooth, compact hypersurface, boundaryless, and via coorientation of sigma. So you have Rn, and you just have some hypersurface with some choice of coorientation of the hypersurface. Okay, and to such a formal fold, you associate a Lagrangian distribution with folds along sigma and Maslov coorientation V. So there's two ways that you could have a fold around a hypersurface. You could either be turning one way or you could be turning the other way. And the Maslov coorientation just determines which of these two ways you're turning. And so it determines uniquely a homotopy class. And it's easy to check explicitly that this class is stably trivial. Okay. So lemma 2 is that the images of these elements under the map, which just remembers the underlying vector bundle, generate the subgroup of stably trivial real vector bundles. Okay. And the proof is that this kernel, by exactness of the fibration, sorry, that is not a map. I stabilized the wrong index. That's better. By exactness of the fibration ON to ON plus, sorry, by the long exact sequence of the fibration ON to ON plus 1 to Sn, this is just the image of pi n Sn under the boundary map, and this is just generated by the tangent bundle to the sphere. And then you use Poincaré-Hopf. So let's see. What I mean to say is that by that argument, that group is just cyclic, and so you just need to check that you can realize any multiple of the tangent bundle, and then that's just an Euler number computation, which you do with Poincaré-Hopf. Okay. So now corollary, notice that it follows that for n equals 137, we have an isomorphism between this kernel and that kernel. And again, I'm sure this was known somewhere, but it's just not difficult to reprove. And why is the corollary? Because, well, one of the lemmas, the lemma 2 gives us surjectivity, and then the previous lemma gave us injectivity. So together we have that. Any questions? I'm almost ready to. I'm almost ready. I'm almost done in the cases n not equals to 137. Okay, let me just maybe finish the argument and then I'll stop again for questions. So now proof of the main theorem for n not equal to 137. Well, just take any element in the kernel of the stabilization map. Then there exists some elements like this with the same image. And pi n minus 1 ON, because by lemma 2, the images of those elements generate the stably trivial elements in pi n minus 1 ON. But then because I have this isomorphism, they're already equal in pi n lambda n. End of the proof. So this is all just to say that you can by hand construct Lagrangian representatives of any stably trivial real vector bundle. And then just by changing some diagrams, that's enough, because there's this isomorphism between stably trivial Lagrangian distributions and stably trivial real vector bundles. So you just construct the elements by hand and show that they're enough by considering the underlying real vector bundles. And then in the rest of the talk, I will explain what you do for the exceptional dimensions. Well, n equals 1 is trivial, but 3 and 7, as far as I can tell, needs more hands-on argument, and that's what my undergrad did. So any questions about the general case? Okay. So this is quite fun. So this involves some octonionic and quaternionic geometry. So the above doesn't work. So for n equals 3, 7, you see the problem is that for n not equal to 3, 7, I'm saying, well, it all reduces to the underlying real vector bundle. But for n equals 3 and 7, there is no underlying real vector bundle. These groups are trivial. So need a different strategy. Okay, and so let me explain what we do. So so we construct a trivialization of the tangent bundle. So this is for all n. We construct a complex trivialization of the tangent bundle to the cotangent bundle. And this you can construct for any n, and it has the following properties. It has the property that, I'll draw a picture in a second, but if I just take the pre-image of the vertical distribution, then this has folds. With respect to Sn. And 2, if I stabilize this, so suppose that I stabilize this. Okay. So let me make myself a little bit more room. So if I stabilize this, I can view the new complex factor as the complexification of the radial direction. So this is, I can reinterpret it as just the cotangent bundle of Rn, take its tangent bundle and restrict it to Sn. And of course, this is just Sn times Cn. So I can view this as a map like this. And so this is trivial as an element of pi n un plus 1. Okay, so you just prove this by hand. So first of all, let me convince you. One is a calculation, but let me just show you what the vertical distribution would be, and you can kind of see that I can give it a fold along the equator. So the tangent bundle to the cotangent bundle of the sphere has a Lagrangian distribution which is trivial as a real vector bundle. And that distribution is obtained by folding the cotangent distribution along the equator. If you take just the cotangent distribution, that's not trivial as a real vector bundle. That has Euler number 2, well, in half the dimensions. But I can take the cotangent distribution and give it a fold along the equator, and then that becomes a real distribution. Sorry, a distribution that is trivial as a real vector bundle. And then you can frame it by hand, and you check that when you stabilize it, it's trivial as an element of pi and un plus 1. Okay, so this is an explicit construction. And now what we're going to do is we're going to compare this trivialization to trivializations that come from quaternionic and octonionic geometry, which are not stably trivial. Okay, so I think what I'm going to do is do the case n equals 3 in detail, and then the case n equals 7 is not entirely identical, but is very much similar. So before I do it, and I mean, I know I haven't explained to you what it is, but I've told you what the key properties of this complex trivialization is. Any questions just about the key properties of this complex trivialization? Is it clear? Let me just take a minute. Let me explain what we're trying to do. There is an obvious element that the stably trivial element could be, namely just folds along a sphere. That is, if there's any justice in the world, that's what the stably trivial element should be. So we just need to show that that is indeed the element that we want. So for instance, let me actually write down what the groups are in this case. Okay, so in this case, pi 3 of lambda is just z mod 2. Z mod 4 to z mod 2 is a unique epimorphism, and the kernel is just the element 2. So what we want to show, what we want to show is that the element 2 in z mod 4 can be represented only with folds. So quaternions yield a trivialization okay, which complexifies to a trivialization of the cotangent bundle of S3. G, which is different from F. This is a trivialization that is a complexification of a real trivialization. So now what we're going to do is we're going to compare them. And if we compare them, we get an element of pi through U3. Okay? And by property number 1, which is this property I drew here, the image of beta in pi 3 lambda 3 is just the element that has folds on a sphere. Let's say V, whatever it is, it's the outwards orientation. So this just has folds. Okay. So what we need is that alpha is twice a generator. Okay, so that's what we need to show. Okay, so alpha is just the image of beta. Okay, is that clear? So again, I've identified the stabilization map. It's the map Z-mod 4 to Z-mod 2. That's just the unique surjection. And then I need to show that the element 2 can be represented by folds. I have a candidate, which I've built by hand, that has folds. And so what I need to check is that it's the correct element. Okay, so let's prove it. And then we're done in the case n equals 3. So because this guy is surjective, because pi 203 is 0, it is enough to show that beta in pi 3u3, which is z, is twice the generator. Okay? Now, pi 3u3 is in the stable range. Okay? So it is enough to show that the stabilization beta hat is twice a generator. Okay? But beta hat, so remember that beta was comparing these two framings together. So beta hat is comparing the two stabilized framings together. And this is just G, since property 2 told me that f hat is 0 in pi 3u4. Okay. And what is well, and what is G hat? This is just the complexification of the element eta in pi 304 that is determined by quaternion multiplication. Okay, so given any unit quaternion, that gives me an orthogonal transformation of R4 by, say, left multiplication with that quaternion. So that's an element of pi 304. And then if you complexify it, that's an element of pi 3u4. That is precisely my G hat. Okay, because I define my G hat in terms of the trivialization coming from quaternion like invariant frame. That frame is induced by quaternion multiplication. And now I'm almost done, but I need to use a classical fact from the 60s, which is that eta maps to a generator of pi 3o. This is a non-trivial fact, but it's a known fact. You can prove it requires some Stiefel-Whitney classes, calculations. You can rephrase it in terms of KO, but in any case, it's something that's well known that quaternion multiplication as an element of pi 304 maps to a generator of pi 3o, which is Z. And then finally, consider the following map. So consider the following diagram. Okay, so pi 205 is 0. Pi 3 lambda 5 is Z mod 2. Both of these are Z. Therefore, this is the map multiplication by 2. I know that eta maps to a generator here, and it maps to 2 by this map. Therefore, the image of eta in pi 3u4, beta hat, is equal to 2. It's twice a generator by diagram chasing, because this map is an isomorphism since we're in the stable range. And that's precisely what I wanted to show. I wanted to show that beta hat is equal to twice a generator. And I just did. So that completes the proof. So let me try and summarize what was the idea. The idea is that you build an explicit trivialization of the tangent bundle to the cotangent bundle of the sphere that is stably trivial. And then you compare that to the trivialization given by quaternionic geometry. And using that comparison, you build an element that only has folds. And then you check that that element is the one that you want by relating it to a well-known element in algebraic topology, which is the generator of pi 3O. And using that fact, you deduce that it's the element that you want. Any questions?
I guess other than using octonions, is there a substantial difference between this and case N7?
Yeah, so maybe let me just say a few words about n equals 7. So in n equals 7, the argument is very similar. It's just the specifics are different. So in this case, there's just everything is trivial and there's just one element. And you also use the fact that octonion multiplication maps to a generator of pi 7O. But the main difference is that when you set up this commutative diagram, so it would be bad if it were exactly the same, because if I get that it's twice a generator, then I'm going to get that it's 0, since I only have Z mod 2. So there better be something different. So let's see. So what I believe is the case is that pi 7 lambda 9 in this case is 0. And so here, this is just a map Z to Z. And so, right. And so instead of concluding that the analogous element beta hat is equal to twice a generator, what you conclude in this case is that the element beta hat is exactly a generator, which is what you want, because here the stably trivial element is just a generator instead of twice a generator.
Nice.
But other than that, the argument is the same. Okay, so I don't know. I'm sorry if that last argument was hard to follow, but I just wanted to kind of show an algebraic topology computation, because maybe I just don't do them that much. So I was happy to do some diagram chasing for once in my life, and I think I'll stop there. Thank you very much for your attention.
Thank you. Questions for Danny?
I have a question. What can be said about a relative version of your results? Say you have a Lagrangian disk and you have a fixed distribution near the boundary, which has no singularities of tangency. Does it follow immediately from your results that in this case, okay, there's a straightforward analog of your main theorem?
If I have a disk and I have a Lagrangian distribution and it's transverse near the boundary of the disk,
yes,
then yes. I think it reduces to the same homotopical statement.
Okay.
Yeah, I think, yeah. They sent me this email this morning. I think even in the case of surfaces, like the relative version that fails is if you only have, say, fold singularities on the boundary, and you have some extension inside, then it's not so easy. Then I think in general it's even false. But if you actually have transversality on the boundary of the disk, then it's exactly the same problem.
Okay. And what about parametric version?
So because the relative version, because the strong form of the relative version with folds on the boundary is false, I think the parametric version fails even in the case of two-dimensional spheres. But that is something that I'm currently trying to understand. I think one can still say something, particularly in 2 dimensions, but even in general, I think one can say something. For instance, it's possible that one might be able to represent the higher homotopy groups of the space of the Lagrangian Grassmannian only with folds, at least in some cases. But like those representations won't be unique because the relative version of the problem is just not true, even homotopically.
Okay, I see. Thank you.
Yeah, and just sorry for my bibliographical remark, which actually I realized was incorrect, because if you only need that the Lagrangian, after applying, which has a generating function, after applying a Hamiltonian isotopy, still has a generating function, this is Sikorav's theorem, which was much earlier than that.
Okay. Yeah, I somehow always get these references.
Terre was a fibration theorem, so it just says that the set of generating function mapping with stabilization mapping to the set of Lagrangian is a fibration.
So just from a one parameter family to an arbitrary parameter.
Yeah, just for one parameter family that was Sikorav's.
I see. Okay. Well,
sorry for that.
No. It's my mistake for not having the references correct. Actually, should change that in the paper. It's one of these weird things because, like, of course, you don't know how far to go. It's like, I think maybe that was for Lagrangians, and then maybe for Legendrians, it was Chekhanov, right?
Yes, for Legendrian, it was Chekhanov. And also he has a nice formula which allows to give an easier proof of Sikorav's theorem. So he has a very nice formula, and there was there was another proof by Brunella, which was later in, using Chekhanov's formula. Yeah.
And yeah, I have a question. Maybe it's a very basic question. So in the theorem, you talk about homotopy sphere, right? Like this. Yeah. But in the proof of n equals to 7, you use octonion. I'm wondering whether like this exotic sphere, like whether smooth structure is important here or just the homeomorphism type.
No, it's not. Even less, even just the homotopy type. So you see, it's because the H principle reduces the problem to something that is just about the homotopy class of gamma. It is fairly easy to reduce it right away to the case where the smooth structure is standard.
Okay.
It's not immediate, but it's almost immediate. Like suppose that I have a homotopy sphere L. Okay. Then what I can definitely, so it's still true that L is the union of 2 contractible subsets. It's just, it might be glued along some bad way, but they're still contractible. So I can still take my gamma and I can make it vertical, say on one of the contractible sets. And now I have a relative problem for a perfectly nice standard disk, which is the other half of the homotopy sphere. And so at that point, you've just reduced it. Actually, you reduced it to the relative problem for the disk that Michael was referring to, which is actually what I consider. So I actually think that's kind of a red herring. It's the smooth structure plays no role in this story.
So it's like you pass to the relative version, and then since the relative version is the same for the exotic and the standard, then you do it for the standard. I see.
That's right. That's exactly right.
Thank you.
Yeah.
And this is kind of, I guess, a little bit related to my previous question, but what if you have something with 3 critical points instead of 2? Can you say what goes wrong?
Yeah, I mean, what goes wrong is there's a couple of things that go wrong, but so you're saying for the arborealization?
Yeah.
Yeah, so I mean, suppose that I have a skeleton that has 3 pieces or something. So maybe at the beginning it looks like this. Then something that you can first do, for example, is try to simplify the singularities of the projection of the, maybe let me give colors, of the red one onto the blue one. Okay, so suppose that you've done that, but then what you then need to control is going to be the singularities of something that projects down here to the base. But that is already itself a singular object. So then when you're trying to control, in particular, what's happening at the interaction of 3 strata, it's a little bit more subtle. And there's, you can, if you fix first the singularities this way, then your hands are tied to then try and simplify the singularities that way. And at least I don't know of a straightforward way to prove the general case using this type of logic. But what we do in our paper with Yasha and David is we use this notion of positivity that basically allows you to get transversality for free once you have it just for 2 strata. You get it for free for the other strata. And that's because of some notion of positivity that, how shall I explain this? So suppose that I have a quadratic form Q which is positive definite, and consider the corresponding Lagrangian. Then claim this Lagrangian is transverse to any conormal. So if I have any conormal, say to a hypersurface, then I claim that if I have this LQ over here, it's going to be transverse, at least in the neighborhood of the 0 section, to this to the conormal of this hypersurface. So in this orbitalization for more strata, what we do is that we achieve transversality for 2 strata at a time, but not only transversality, we achieve transversality in a positive way. And because of this simple observation, that actually implies that for the rest of the strata, you get transversality also for free. And that is kind of how we control that story. But without this kind of thing, I personally don't know how to do it.
Thank you.
There is a secondary difficulty, which I think is less serious, which is that even assuming that this issue of, well, I don't know if it's less serious, but I think it's less serious. Even assuming that this issue of multiple strata wasn't a thing, suppose that you have some very complicated skeleton and a whole bunch of handles and whatever, then you would need to know that the obstruction to applying the H principle vanishes on each of the handles separately. Existence of a global polarization tells you that somehow overall there's no obstruction, but if you try to apply the strategy inductively, you would need to know that at each stage of the induction, the appropriate obstruction vanishes. And for all you know, it could be that here there's an obstruction, but it canceled later on. So maybe you didn't organize things right. And so I don't see of any obvious way to arrange the logic so that you know that from some global hypothesis at every stage of the induction, the H principle can be applied. So those are 2, I think, serious issues, but those don't appear when you just have 2 strata. And so that's why I just gave that application, because it's very straightforward.
Thanks.
Well, if there's no more questions, I think we should thank Danny again.